Welcome to Derivability. We're going to take a look today at inverses of hyperbolic functions. This is the second in a series of several videos I have done or will be doing on hyperbolic functions. Okay, so let's start off by taking a look at the hyperbolic cosine function. Got a little graph of it there to show you. And we want to figure a formula for its inverse. Okay. Now, a couple of technical things first. One is this function is not one-to-one. Okay, so for instance, we can't technically have an inverse of a function that isn't one-to-one. All right, and then the way we know if something is or isn't is we apply, say, like a horizontal line test here. Okay, what we see is that any horizontal line, at least above y equals 1, is going to intersect the graph in two places. So when we flip this graph, if you will, about a diagonal line, y equals x, it won't even be a function, and that's our problem here. Okay, so what we need to do technically is we need to, for purposes of finding an inverse, make it into a one-to-one function, by restricting its domain. Okay, well, right now the domain of the hyperbolic cosine function is the set of real numbers. All right, and if we chose to eliminate the negative real numbers from the domain, okay, and I'm going to try to kind of somewhat inartfully erase part of this graph. Okay, I think you can see what I'm trying to do, even though I'm not doing a perfect job at it here. Okay, but what you're finding now is that what we have left, this restricted domain of the positive real numbers, and also along with x equals 0, now we do have a one-to-one function. Okay, so strictly speaking, we can talk about the inverse. Okay. All right, well, what is this inverse going to be, or what is it going to look like? Okay, well, you guys know that if we reflect this about the line y equals x, it's going to look something like that. Okay, before, if we reflected that, we'd get some stuff down here. Okay, and of course, then in red, that wouldn't even be a function in the first place. Couldn't do that. Okay. All right. Now, on the other hand, you might say, okay, wise guy, what is the inverse function? All right. Well, in fact, it is the inverse hyperbolic cosine. Y equals cosh inverse x, if you like. If you want to say it that way. Okay. And that's sometimes that's actually more than good enough. Okay. If you have a calculator, spreadsheet, computer algebra system, whatever, or just like a really smart friend, you can plug in any number here and get a decimal number for y. That's good enough for a lot of things. Okay, what if you do not have a calculator that has hyperbolic functions on it? Okay, so that's really one of the purposes here is to provide us a little fallback just in case your calculator doesn't have that capability, but also, to provide maybe a little insight into what's really going on here. Okay, so let's do that now, starting with the hyperbolic cosine. Okay, well, let's remember what this really is. Okay, this hyperbolic cosine, have x's here instead of u's today. Okay, this hyperbolic cosine is defined in terms of exponential functions, as are all the hyperbolic functions. Okay, so if I can somehow solve this for x, okay, ignoring this middle number here, if I can solve for x in terms of y, well, that will be the same as an inverse hyperbolic cosine. So let's march in that direction and see what we can do here. So I'm going to multiply both sides by 2. So we get 2y equals e to the x plus e to the minus x. Now you might be asking, well, how can we solve this for x? To get inside that exponential function, you might need to do a logarithm, but how do you do a logarithm of one exponential function and not the other. Okay, well, let's multiply through this whole thing by e to the x, and what that will do for us, it will give us a quadratic equation in the variable e to the x. Okay, so I can arrange this. You might imagine if it's going to be a quadratic, then I have to write all the terms on the same side of the equation. Okay, and really I want to think of this e to the 2x as e to the x squared. Okay, and in that case, I have a quadratic in this variable e to the x. Okay, well, you probably, if you're watching this video, if you know about hyperbolic functions, or you want to know, you probably know our quadratic formula here. So if we apply our quadratic formula, we're going to get e to the x equals, okay, big fraction, opposite of b, so 2y, plus or minus the square root of b squared, minus 4ac all over 2a. Okay. All right, now what we have here is with something where we, inside this root, we can factor out that 4. And then if we bring that 4 outside of the root, we get a 2. Okay, and we see here very nicely that we can kind of factor out, cancel those 2's. So we're getting e to the x equals y plus or minus the square root of y squared minus 1. All right. Okay, and then finally, to solve for x here, I want to take the natural log of both sides. Okay, and now that I've inverted in terms of x and y, okay, I can actually say for the inverse function, y equals natural log of x plus or minus square root x squared minus 1. Now we have a bit of a problem to work out here with this plus or minus, because if we're solving for y, and we have restricted the domain like I've shown, there could only be one answer here. Okay, so it turns out that we can only have the plus sign here. Okay, and because I have successfully inverted, this actually is another expression for the hyperbolic cosine inverse of x. Okay, now if you take a look at that square root, x squared minus 1 inside the square root, what you'll see is that, just generally from math, we would see that the absolute value of x would have to be greater than 1. Okay, of course, in this picture, in red right there, there is no other option other than x greater than 1. Okay, we can't have x less than -1, which would be the other option. Okay. All right. Also, I think what you would find is if you had this plus or minus here, if you included a minus, what you would end up getting is y values down here. Okay, which again, that does not work. Okay, if we're going to have both of them, you can choose one or the other, but we can't have both. So we choose that upper part that I've drawn in the solid red. Okay, so if you have a calculator that does both hyperbolic functions, then of course I'm assuming your calculator does logarithms and exponents. Okay, so try, just pick some value of x here, maybe a couple different values of x. Try both versions, and if you have to go to a computer or spreadsheet or something to do the inverse hyperbolic cosine, and you do the logarithm on your calculator, you can just find out. You can hopefully verify. They give you the same number for lots of different values of x. Of course, values of x greater than 1. Okay, just a final bit of insight here. It kind of makes sense. Think about this. that if the hyperbolic cosine, or any hyperbolic function, is defined in terms of exponentials, then its inverse probably should have something to do with a logarithm. Okay, kind of makes sense, maybe more philosophical sense than anything else. All right. Okay, so if you want to hold on a minute, I'll get the screen ready and we'll talk about the inverse hyperbolic sine. All right, well, here we are again. So here is a sketch of y equals sinh of x. Okay, notice in this technical sense, this is already a one-to-one function, so there is no need to restrict the domain. Okay, what we can do is we can imagine this, kind of reflected in the diagonal line y equals x. Again, if you'll pardon my poor artwork here. Okay, what we should end up with is something that we can call y equals sinh inverse of x, inverse hyperbolic sine of x. Okay. Now again, the goal is to kind of whack through some algebra and see if we can come up with some sort of exponential or logarithmic formula for this. In fact, I am willing to bet that if you want to pause the video here, you can probably crank this out yourself and watch the video afterwards to see if you figured it out. Okay, but of course, keep on watching if you want to see how this works. So once again, what I want to do is I want to solve this equation for x in using the exponentials in terms of the y. Okay, like I did before. So let's just go ahead and do that. So I have 2y equals e to the x, subtract e to the minus x. Okay, and the same procedure that we tried before is indeed going to work. Okay, we're going to get a quadratic equation in the variable e to the 2x. Okay, and then using our quadratic formula for that. Okay, very much the same thing here. Okay, and I'll just kind of cut to the, skip a step or two here, because it's very much the same sort of thing that we did for the hyperbolic cosine. Okay, so we get this formula, and then to solve for x, take the natural log of both sides. Okay, now as it turns out, once again, we only get a plus here. We only use the plus. Okay, the reason for that is if we had a minus, we would be taking the natural log of a negative number. That doesn't work, as you know. Okay, so when I invert x's and y's now, y equals ln of x plus, only the plus now, x plus the square root of x squared plus 1. Okay, and this is the same as the inverse hyperbolic sine of x. Okay, now in this case, you can plug in any real value of x that you want. If you plug in positive values of x, you're going to get positive values for y. Okay, also it turns out here if you plug in negative values of x, I believe you're going to get negative values for y. Okay, this works out very nicely. So this inverse hyperbolic sine will give you any real number. Okay, the inverse hyperbolic cosine will give you positives, and if you're interested in the negatives, you can just do those instead. Okay, the formula does not give you those using different values of x's. Okay, all right. So once again, if you want to convince yourselves, try maybe graph both of these functions on your calculator on an online graphing program like Desmos or GeoGebra, several others. Okay, plug in some x values and just see that both formulas really do give you the same thing. Okay, all right, we'll do one more here in a moment, and that is the inverse hyperbolic tangent function. Okay, well, welcome back here. There are other hyperbolic functions that match the trig functions, and they're defined similarly. Okay, so for this hyperbolic tangent function, if you like, we can define this as the ratio of the hyperbolic sine with the hyperbolic cosine. Okay, its graph looks like this. It actually, if you're thinking it has asymptotes at y equal plus or minus 1, it does. Okay, and in terms of the exponentials, okay, as you might suspect here, okay, the 1/2s nicely cancel. So in terms of exponentials, you might say this is our definition of the hyperbolic tangent function. And once again, if we can manage to solve this equation on the far left and right sides here for x in terms of y, that will be, it turns out, a logarithmic representation of the hyperbolic tangent function. Okay, so let's get on it here. So what I'm going to do is I'm going to multiply both sides by the denominator containing the exponentials, the sum of the exponentials. Okay. Next, what I'm going to do is, as before, is multiply through both sides by a factor of e to the x. Okay, with the goal kind of being to get a quadratic, although it's actually going to be just a little bit simpler than that. Okay, so now let me distribute the y through the left-hand side. Okay, and let's see here. I'm going to get my exponentials on the same side. Okay, and I can factor out an e to the 2x. Okay, so what I'm going to get here is e to the 2x equals, it kind of looks prettier if I write this 1 plus y over 1 minus y. 2x then is going to be a natural log. And then solving for x, 1/2 natural log 1 plus y over 1 minus y. All right. Now I can swap the x and y here and write y equals 1/2 natural log, okay, 1 plus x on top, 1 minus x on the bottom. Okay, and this should be the same thing as our inverse tangent function. Okay, so if I reverse the, or if I reflect my graph up here about the diagonal line y equals x, okay, I should expect to get, excuse me, an inverse tangent function, hyperbolic tangent function, something like this. Okay, now if you want to, I don't really prefer doing this myself, but this 1/2 can be brought in as a power, 1/2 power, basically a square root inside the logarithm. You know, I don't really like doing that myself, but I've seen it both ways. Okay. All right, so those are kind of the three main hyperbolic functions. There are three others. In fact, I'm sure you already know the names of them by now. Hyperbolic secant, hyperbolic cosecant, hyperbolic tangent. Okay, I think what I'll do here in a moment is pause again and then just kind of collect up some of these formulas, and then the formulas for those other three so-called reciprocal hyperbolic functions, the secant, cosecant, and cotangent. Get down the formulas for the inverses of those. Okay, and again, for the formulas for the inverses of the reciprocal functions, I think you can probably manage to figure those out by yourself at this point, having seen these others done. Okay, so I hope this gets you situated to try the next important thing that you are working on in your studies. Okay, here's a summary of what all 6 of the inverse hyperbolic function inverses are in terms of logarithms. Okay, the first 3 we went through and proved. The last 3 you can actually easily prove if you go back and do the original definitions in terms of the exponentials, or maybe you know a little shortcut doing something with the x in one of the first three formulas. Maybe you can figure that out. Okay. Now, once again, some of these require a little bit of care in appropriately restricting the domain of the original hyperbolic function. But once you do that, then it's pretty straightforward, I believe. All right. So, anyways, thanks for hanging out here and staying until the end of the video. Appreciate it if you could share this one, like, subscribe, do all that cool stuff for me. My first hyperbolic video got a very good response so far, and so I hope that the rest of the videos in this series will be of interest to you and your classmates as well. So thanks again, and we'll see you for hyperbolic number 3, hopefully sometime soon.